Hello, everyone, ladies and gentlemen. My name is Mian Zhou, and I'm from School of Computer Science and Engineering, Tianjin University of Technology. It's a university in Tianjin, and in this university we do a lot of computer vision, and we have a MOE, Ministry of Education laboratory in our school, which is called Computer Vision and System. And today, it is my honor to give you a presentation to this computation, what we call CalmCar MTMC challenge in WAC AV Vision workshop. Okay. And later, and this is our presentation of what we have done in this competition. And this work is done by me and my students, First of all, let's introduce this problem. This problem is to design algorithm to track multiple targets and multiple cameras. That is, multiple camera, multiple target tracking. So it's called MTMC. The MTMC has a long history in the computer vision. The famous one is in the potential tracking. So we have seen a lot of potential tracking algorithms or data sets in computer vision. The famous one you may know is from Duke Universities. But however, in the vehicle trackings and in the vehicle trackings, there seems not much research work. Here, and with this opportunity, I would like to thank this challenge organizer, and they have contributed a lot to this in the computer vision society for the multiple target and multiple camera tracking on vehicle. The multi-target and multi-camera tracking systems normally can automatically track the multiple vehicles using an array of cameras. This challenge, we are required to design a robust MTMC tracking algorithms, which is targeted at vehicles where the same vehicles captured by different cameras possess the same tracking IDs. And this challenge also gives us a large scale of training set with 4 different views, each of which include around 200 annotated RGB image, where labels covers the type of vehicle, tracking IDs, and the 2D bounding box. The evaluation metrics are identification, precision, and identification recall. And here is the result of our work. So we can see the object is tracking correctly and precisely. And we can see there's the total of 4 onboard cameras on the car, which you can see the road direction in the front view of the camera. This is the front view, and this is rear view, and this is left front view, it is left rear view. And we can see this in the left front view and the left rear view, we have some distortion. You can see here there's a big distortion. However, in the front and rear view, there's small distortion. The main task of this competition is to take other vehicles appear in the camera as targets, assign an ID to each target, and the ID of same target always remains unchanged. To achieve the multi-target tracking and the multiple camera, 3 problems need to be solved. Problem 0, tracking a single target in a single camera, which is typically the tracking problem in our textbook. If you look at the textbook, I always talk about this Kalman filters, particle filter, and in the only one object, one target, and in a constant camera. And the question number 1, that's tracking multiple target in a single camera. So we have more than one target. So how do we do the tracking instead of single target? So that we need to do one more thing additionally. This is to do the data association. Normally we use some methods such as the Hungarian algorithms to sort out this data association. Question number 2 is to unify the IDs of the same target and different cameras. And this because we have different cameras, several cameras, and we need to tracking cross cameras. For example, one object appearing on the camera and another object appearing on other camera. There are 2 different objects, or they're just the same objects. This is the questions. And another situation is one object appearing in one camera, and after a few seconds, and it's disappeared. And after a few seconds later on, another object appears in another cameras. So are they same, or a new object came in? So that's all sort of problems is complicated and need to be sorted out. The following is a beautiful introduction to the research status of the fields in the industry. So I did not write in this part into the PPT, but I still would like to introduce it to you. And the first is in the traditional sense, the problem and the characteristics of multi-target tracking. Number 1, the number of the target change over time. So in a scene, so we have many targets, and some target may disappear, and some targets may appear in. So the number of the target changes over time. Number 2, estimate the continuity state of all current targets. In some cases, so we when we doing tracking, the movement of the object or the target is the linear. For example, for the car moving and the airplane flying in the sky, the movement normally that they are linear. But however, in some other circumstance, the movement is not linear. For example, the gesture, the hands movement. So how we do the modeling the non-linear situation. 3, the describe combination problem of data association. So in the data association, we need to assign the detection to the tracker. So that's give our problems. 4, the data set contains only one category and one cameras. And in the problem and the characteristics of multiple character and multiple multi-camera unification. One is the same target in the same category has different size and different cameras. Okay, so because in different cameras, even the same object, they have a different pose respect to this camera, and a different distance between different distance to this camera. So it's decompose the different sizes. Also, even the multiple cameras, but due to the distortion, the same target may look different. Okay, or the different. 3. Need to analyze and match the multiple categories. 4. Its dataset provides the direct detection result of each target. When we just starting to get to this computation, we think about the use of the traditional machine vision methods. The traditional machine vision method is convert and merge the 2D image coordinate into 3D world coordinate, and then the tracking object by 3D coordinate. Okay, we hope, first of all, we hope we can achieve this multi-target, multi-camera trackings by traditional computer vision methods. But our implementation plans as follow. First, through the perspective transformation method, each camera image converted into a top view, and then the small top view are obtained, is cutted, and we stitch them into a big top view and big, large, complete top view of road. Okay, and so we need to find the homographic transformation matrix from the front view to top view, from the rear view to top view, from the left rear view, left front view to top view. So, and we calculate to generate like a bird eye image or bird eye view, and we stitch all the image together, and next we perform a single camera multiple target tracking on top view of road obtained in the previous step. After obtaining the trajectory of each target, unifying the IDs for each target, and finally convert back to the original perspective views and get IDs of each goal, and we hope to complete this computation in this way. Unfortunately, this approach did not achieve its design effect. According to the large of the top computed top view we got earlier, and we have plotted our objects on this map in the maps. So we can see the each detect target in the world coordinate systems. Each point in the image represents the target and its position. Some vehicles in the image repeated, and also there are some unreasonable location distributions among objects. Through the analysis and the summary, we found the perspective conversion. This kind of bring some disadvantage. So why it failed? It's because the perspective transformation error is large. It depends on the first of all we do the perspective view to top view, and then top view back to the perspective view. So in each transformation it generates error. The accumulate error will also be large. Number 2, sometimes we have the video jet problems in problems, and it's magnified and to rule out to rule our results, because we have set up transformation, the transformation from perspective view to top view. That's and we also can compute the transformation matrix. But this confirmation is constant over the whole process. But however, in some circumstance, for example, if we cast go up here and go down here, this transformation has been changed. The characteristic of the matrix were changed. But however, when we do the setup, we set it constant, so it makes error. And the third one is we do the perspective transformation. It also cause the surface deformation of the vehicle, and the model cannot obtain the sufficient features. The above reason prevent us to think this it doesn't work. So and then we choose to implement our multi-target, multi-camera trackings using sometimes new technology, deep learning, and we use the IOU feature and VID, and re-identification. First of all, to consider the target is tracking under a single camera. The IOU matrix and the characteristics distance matrix are established according to the track T-1, calculated at the previous moment, and the detection T monitored at the current moment. We use matrix modification on the IOU matrix and the characteristic distance matrix to find the new A matrix. Finally, the Hungarian algorithms is to use the solve the M matrix and the trajectory track T, and a single camera at time T is obtained. Next, according to the trajectory track C1 in the camera C1 and the trajectory track C2 in the camera C2 obtained in the previous step, subtract the features from each trajectory track, calculate the corresponding characteristics matrix, distance matrix, and judge the distance between the characteristic matrix. The Unifying and Unifying ID is assigned to the similar target. There's two ways. One is how we solve the single target, single camera, multiple target trackings. We can use the IOU, combine the VID, to combine some features, and then it's the traditional method. And the other one, the second, is how we sort out the cross camera tracking. We use the identification pattern methods. The specific approach is to recreate our data set according to corresponding ID of all target in the video. So here we can see the data set we generate for VID identification is the 131 object. Each target is cut out according to the bounding box in the video and classified and saved. The VID network is trained with ResNet 50 as the backbone network. The number of output euros and last layer of network is equal to the type of all video target in the training set. In this test, the output is the fully connected layers is used as a feature vector of the target and is solved according to the Euclidean distance. Since the IOU value of the same target is usually greater than that of the different target between the adjacent frame, you can start with IOU according to the tracking target T of the previous frame and all detection target D in the current frame. The IOU is equal to these two frames. The intersection part is divided by and merged part. Thereby establish the IOU distance matrix and IOU. Okay. And then because there are some small targets, so the IOU may not work. So we use the features distance matrix and features to calculate the differences. IOU distance matrix, IOU, and the feature distance matrix and feature obtained above are subject to element modification calculation to obtain a new matrix A, and then we use the Hungarian algorithms to obtain the optimal solution of the main matrix is its data association. So to find where the detection belong to which tracker. In order to correlate the target ID and the different cameras, the feature matrix M feature established for the different targets after association, and each camera is calculated according to Hungarian algorithms to obtain the optimal solution. The multiple camera, multiple tracking unifying approach is almost the same in principle as the previous single camera multi-target unifying approach. And here is our result. So in the IDF matrix and MOT metric, and in the whole process there are 131 objects to be tracked, but we only missed the 4 objects. So for us the result is pretty is good. Okay. And finally, we would like to, because the time is the time is short, so we would like to investigate more methods to this, but time is limited. So for the future work, I would like to talk about some future works. And the first ones, during the training process, we found when the road condition is very largely, the IOU matrix may produce large errors specific to the training set. That is, when the car and the tracking target turn at the same time at the intersection, the motion models is not very good at this time, and the trackings may fail. At this time, we would like consider using STM, and which is special on the recurrent neural network. Compared to the ordinary RNN, STM can perform better in longer sequence. It can mainly solve the problems of gradients disappearing and gradients explosion during the long sequence training. We also found that due to the distortion of the camera and the occlusion of the object, a lot of noise will be generated, and the object may be blocked by another object. And we think we can consider matching based on local features. The main idea of the local-based method is to use image segmentation to obtain large objects, to obtain local or area features, and then to combine the global features to represent our object. The car images can be divided into the multiple parts from top down, and the features are respectively taken for each part. And finally, the obtained local features and the global features are fused together as the final vehicle image feature. And finally, it is the end of presentation. Thank you for your listening. And by this opportunity, I would like to thank you to the event organizer and also the people who has contributed to this challenge, because you provided such a good data set with a very accurate notation. Thank you very much.